Just to recap 24.1, the size of the atom is 10 to the minus 10 meters or 1 angstrom, where 1 angstrom is 10 to the minus 10. So that's the size of the atom. And the radius is about 10 to the minus 15, which is approximately 1 femtometer. So femtometer stands for 10 to the minus 15. Now the three conclusions of the Rutherford alpha scattering experiment is that because most of the alpha particles went straight through the gold foil, most of the atom is empty space. However, some of it got deflected, some of it came back more than 90 degrees. So around about 2000. So is it 1 in 2000? So around about, yeah, so 1 in 2000 alpha particles were scattered. But then about roughly 1 in every 10,000, it was more than 90 degrees. So the conclusions from that is that the nucleus was positive because it was repelled. The charge of the nucleus is positive. That means it's repelled by the incoming alpha particles, and therefore most of the mass is concentrated in the nucleus. Now, you would be able to work out the kinetic energy of the alpha particles, and because when the alpha particles were fired towards the nucleus, the kinetic energy will be converted into electrical potential energy, and then you would be able to work out the distance of the approach, the distance of the shortest approach. The nucleus, we've got protons and neutrons. Now, we need to know the definition of isotopes. Now, hydrogen has 1 proton in the nucleus and 1 electron in the outer shell. For helium, you have 2 protons and 2 electrons in the outer shell. So depending on the number of protons, that will tell you what element it is. So different elements have different number of protons. However, you can have different number of neutrons, but then that will still be the same element. So for example, hydrogen, they all have the same number of protons, which is 1, but you could have 2 neutrons in the nucleus, that will be tritium, and if you have 1 neutron, that will be deuterium. So the word isotope is the same element, but it has different number of neutrons. Now the atomic mass unit, that is defined as 1/12 of a neutral carbon-12 atom. So experimentally, that is 1.661 times 10 to the minus 27 kilograms. Experimentally, the radius is proportional to the cube root of the mass number A. So the radius is proportional to the cube root of the mass number. You can also say that the radius is proportional to the cube root of the nucleon number. Now, the word nucleon describes the subatomic particles in the nucleus. So, for example, protons is a nucleon and a neutron is a nucleon. So the mass number is the total number of protons and neutrons, and we can also say that is the nucleon. Now, quick electrons have a de Broglie wavelength of 1 femtometer. So there is evidence that electrons can travel as waves from diffraction, and because of this diffraction, we can work out the radii of atoms. So the equation is R is equal to R naught, where R naught is 1.2 femtometers roughly, multiplied by the cube root of A. So the cube root of A is the cube root of the mass number, or the cube root of the nucleon number. So the density of the nucleus is about 10 to the power of 17 kilograms per meter cubed. If you compare that to the density of water, that is 1 kilogram per meter cubed. So if we look at the nuclear notation, A is the mass number, or the nucleon number, where it is the number of protons plus the number of neutrons. And Z is the atomic number, or the proton number, and that tells you the number of protons. So to work out the number of neutrons, it is A minus Z. Now, can you check if this is the correct steps? So, what is the approximate density of helium-3 nucleus and the atom? Now, you know that the volume of the nucleus is 3 over 4 pi r cubed. So if you write 4 over 3 pi, and then remember if we go back to the previous slide where r, the radius, is equal to r naught a to the power of the third, we get 4 over 3 pi brackets r naught a to the power of third, and all of that cubed, because you're using the equation 3 over 4 pi r cubed. So putting that in, you get 4/3 pi r naught cubed times a, where a is the mass number or the nuclear number. So the volume is 4 over 3 pi. Now remember, R naught is the constant, which is 1.2 femtometers cubed. And then we multiply that by A. And in the question, it says helium-3. Helium-3 tells you the mass number or the nuclear number. So we multiply that by 3. So in the end, we get the volume as 7.24 times 10 to the power of minus 45 meter cubed. The approximate mass of the helium-3 nucleus is 3 multiplied by the atomic mass units, and U was 1.661 times 10 to the power of minus 27. So the approximate density is mass over volume, so you do 3 times 1.661 times 10 to the power of minus 27 kilograms, all of that divided by the volume, which is 7.24 times 10 to the minus 45. So mass over volume gives you the density, which is 6.88 times 10 to the power of 17 kilograms per meter cubed. And the density of the helium-3 atom, you would do 4 times the atomic mass units, and then you divide it by the volume of that atom. Now you do, so the volume of the atom is 4 over 3 pi r cubed, where we approximate the radius of the atom as 10 to the power of minus 10, because the radius of the nucleus is 10 to the minus 15, and the radius of an atom is roughly 10 to the minus 10. So we do 4 times u divided by 4 over 3 pi r cubed. We substitute r as 10 to the minus 10, and we end up with 1,586 kilograms per meter cubed. Let's work out the Coulomb attraction or repulsion between two protons in the nucleus. So let's assume that the radius is about 10 to the minus 15. The separation between the two protons is also 10 to the minus 15. So we put that into Coulomb's law. F is equal to K times Q1 times Q2 divided by R squared. And you know that K is 9 times 10 to the 9. The charge of the proton is the same as the charge of the electron, which is 1.6 times 10 to the minus 19. But because you're multiplying two protons together, you're squaring it, and then you divide by 10 to the minus 15, all of that squared. Now you end up with 230.4 newtons. That is a lot of force between two protons in the nucleus. Because if you use Newton's law of gravitation, you end up with 10 to the power of minus 34 newtons. So it is much smaller. The gravitational force between two protons is much smaller than the electrostatic force between two protons. So what is causing the 230 newtons repulsion in the nucleus? Now we call this the strong nuclear force. In other words, if you use Coulomb's law between two protons, there must be another force keeping the two protons together, because naturally two protons are repulsive. However, something must be causing the two protons to come together. Right, so this is the graph of the force between two nucleons. So if you look at the graph, if it's less than 0.5 femtometers, the force between them is very repulsive. Because if we assume that positive and positive is repulsive using the Coulomb's law, if you multiply two positive charges together, you get positive, and they are repulsive. If you have a positive and a negative, because opposites attract, you have an attractive force. So in the positive region, it is repulsive. In other words, nuclei are not equally squashed as the nucleons cannot move closer together. However, above 0.5 femtometers, it becomes attractive. So a separation of greater than 0.5 times 10 to the minus 15 meters results in a smaller force of attraction. It gradually increases in magnitude, but negative, and then after about 1 femtometers, it goes back to 0. So one that is virtually zero by about 3 femtometers. So the strong nuclear force is a very short range force. Now, the line for the strong nuclear force cuts the x-axis at about 0.5 femtometers, and then it approaches very closely to 3 femtometers. So make sure you're able to sketch this graph and then label the axes, so 0.5, 1 femtometer, and 3 femtometers. And the maximum attractive force is when the separation is about 1 femtometer.